So we're going to go over Chapter 1, Section 5, Applications and Modeling with Quadratic Equations. And these are basically using or solving problems that occur in real life or could occur in real life that require quadratic equations to model them. And literally what we're going to be doing is we're going to be doing what mathematicians always do. So we're going to extend concepts. So this is just a straight line, and a straight line is a one-dimensional object. It has one dimension. What does it mean by that? If you were traveling on this line, you can either go forward or backward, but not up or down, or in or out of the page. And the measurement of a line is its length. So here, if I say, okay, I want to go from here on my number line, I chose the wrong thing, here on my number line to down here on my number line, that's going to have a length. And the thing about a length is that it is a positive number or zero. I guess there is in some places and in some occasions we could talk about a negative length, but in general a length measurement in most contexts is always positive or zero. And this is a one-dimensional measurement. So let's move up a dimension. So let's go up a dimension to 2 dimensions. Well, 2 dimensions are going to be modeled in what's called, I don't know why I keep trying to draw a line without the computer helping me, are going to be modeled using the 2-dimensional Cartesian plane. And this is especially for you who will go ahead and go into calculus. So the x and the y represents x is one dimension, y is another dimension. And what would be a typical, this is 2 dimensions. And a typical dimensional measurement that we might like to make in 2 dimensions would be something like an area. So here I have a square. I don't have to place it right at the origin, but notice I can draw an object that is more than just a line. So that's supposed to be a square, and its area measurement would be all of that area I just colored in. So area, if this turns out to be the length of this side of my I guess I could just call it a rectangle, and that the width, then the 2-dimensional typical measurement is area, which is length times width. Of course, there's other types of areas. I could literally, this certainly is something that exists in 2 dimensions, and when I fill it in, it also has an area, and it doesn't have a clear length or a clear width. Calculus was actually designed to find out what some of those areas are. This one would be extremely difficult to calculate, in particular because that little bitty dip right in there and some other aspects of it. But one way or the other, we're going to just deal with simple things, and it's going to be area is going to be length times width, and that's a 2-dimensional measurement, 2 dimensions. So going on down, how are we going to go beyond this? We're going to go into the 3rd dimension here, and I've not drawn this for a while, but we're going to have our 3rd dimension is going to be It's funny how we can represent the third dimension in a three-dimensional space. So in this case, this is my x, this is my y, and this is my z. And the important thing here is if we wanted to measure something, so let me write it here, 3 dimensions. So the common measurement here is that of a volume. It's a three-dimensional measurement. So a typical volume might look something like this. Just bear with me as I draw, or fast forward. Actually, none of this is required. But it's kind of fun because I'm going to show you something else. I'm literally treating you just as if I would. This is exactly what I do in my. That was a bad choice. Let me make it up here. There we go. These need to be connected. So that's a box. Well, it's supposed to be a box. It's not quite a box. And its dimensionality is that of a volume. So you can imagine if you have an aquarium. Let me just do one outside of these coordinates. It'll be much easier. I'm just going to freehand it because I'm taking up too much time doing this. It's fascinating as it is. It'd be something like this. Really, you see why I want to use the computer to aid me to draw. And the dimensionality of it is going to be as if it were a solid and everything was filled up. Think about an aquarium. I actually give you some examples of volume. Think about the amount of water that fills an aquarium, the size of a room in the house, how much air is in a house, the amount of sand in a sandbag. That's the volume. The really cool thing about this is we can actually extend our dimensionality to go to 4 dimensions. So we have a 3-dimensional cube, and you can imagine a 3-dimensional cube much better than I can draw one. But in math, we have 4-dimensional cubes, 5-dimensional cubes, 6-dimensional cubes, etc. These cannot be pictured because the dimensions are actually length dimensions. And the only thing we can do is model them mathematically. And what I did is you can literally go online. These are called hypercubes. And people, so you can see all of these choices right here. Hypercubes starting from dimension 0 up to dimension 6. But let's just do a 4-dimensional hypercube. So someone actually created a mathematical program in the mathematics for it so that we could imagine what a 4-dimensional cube that was rotating would look like to us poor people stuck in 3 dimensions. And it's really kind of trippy. So this is literally what we would see living in 3 dimensions if a 4-dimensional cube existed and we're rotating, and of course part of that rotation is visible in 3 dimensions. So that's kind of cool. Anyway, we get back to the problem at hand. You can do hypercube, whatever. I think sometimes they're called tesseracts. I'm not really for sure all of the different names that they have out there. But we want to go ahead and we want to solve some problems. That was just the prelude, the overture. Many of you will just jump right to this part, which is absolutely fine. But math has some beautiful concepts. And the concepts of dimensionality extended beyond what we can sense with our own 5 senses is excellent. We live in a 4-dimensional world. 3 dimensions of space and 1 dimension of time. And all of the beautiful, beautiful, unintuitive and surprising results of that connection that's called space-time with Einstein's just special theory of relativity and the concept of time dilation. We couldn't understand the universe without it. And this is just special relativity, nothing to do with general relativity, and nothing really to do with quantum mechanics, which is its own weird thing. But here's back to, I guess, maybe the boring part. I'd say really, you cannot tackle, if you're learning to play, say, the violin or the piano, you can't play piano concerto until you learn to play Old MacDonald. So we're at the Old MacDonald stage and working our way up. So since these solutions, you'll be doing these in my math lab, negative solutions usually don't make any sense, nor do complex valued solutions. So when you encounter one, just throw it out. We won't always throw it out, but if we can't make any sense of it, we throw it out and just take the positive solution. Sometimes 2 solutions will actually make sense. We'll see that later on. So let's do example 1. A piece of machinery produces rectangular sheets of metal such that the length is 3 times the width. Equal-sized squares measuring 5 inches on a side can be cut from the corners so that the resulting piece of metal can be shaped into an open box by folding up the flaps. If specifications call for the volume of the box to be 1,435 square inches, find the dimension of the original piece. So it's hopeless to even try to do this without drawing a picture. And for those of you who are panicking, I rather imagine people who have taken metal shop and have made one of these boxes can picture what's going on here. The rest of you have no freaking idea. It would take you maybe an hour just to figure it out. So if you're ever given this on an exam or in my math lab, they will provide you with the picture. And I tried to draw one. It was, my drawing abilities. And this particular program I'm using, it's excellent because it's fast. It doesn't take up a lot of system resources, so it loads up fast and it doesn't slow the computer down. But I actually went to our textbook and grabbed the relevant picture. So here is the original sheet of metal outlined in blue. So let's look here. Let's now that we've got it up. So here, outlined in blue, is our original metal sheet. This length here is the length, and this is the width. And they say that the length is 3 times the width. So they're calling this the width, and x is the width. So in this case, let's just start writing down what we have. X is equal to the width, and 3x is equal to the length. And this is for the original piece of metal. And we know the volume is equal to length times width times height. So we have to find a height measurement. And we're also given that the volume is 1,435 cubic inches. So that's all going to be some important area. But we also know that if they cut out of the corners of this box little squares on each corner 5 inches apiece. And when they fold these flaps up, you get what's down here. So what we want to know is, we know the volume of this down here is we want it to be 1,435 cubic inches. So we want to know what is the dimensions of our original rectangle. So once we find the value of x, we will find the width, and then multiplying by 3x, we will find the length. So literally, we're looking at something that is a volume and using information from the volume to find the dimensions of a two-dimensional object that was used to make a three-dimensional object. So we have to find, notice this inner little bitty rectangle here. So let's find its dimensions. Well, I'm cutting from 3x. I'm snipping off 5 inches here and 5 inches here. So that dimension is going to be 3x minus 5, which is 3x minus 10. And we're going to do the same thing down here. This length is 5 and 5, which is 10, taken away from x. So that's x minus 10. So we have the following. We have volume is equal to length times width times height, which is equal to 3x minus 10. Our height, when we fold these flaps up, the height will be 5 inches, times x minus 10 times 5, and that's, we want it to be 1,435 cubic inches. So this is the equation, So literally this is the equation we're solving. So in standard form you would probably write it this way. 1,435 is equal to 5 times 3x minus 10 times x minus 10. So the first thing we want to do is we want to divide through by 5. So 1,435 divided by 5 gives me 935. Let's check that. Well, I did it with the calculator. I don't feel like, I'm just going to check it. I did it earlier. 435. I've already spent so much time talking about dimensionality. I don't want to do this in long division. 1435 divided 5 is 287. So I'm glad I did that. That didn't seem right to me. So it's 287. I'm actually changing the way I have in my notes. Now that's, so now you have 287 is equal to 3x minus 10. So let me just show you again what I'm doing. I'm dividing both sides by 5. The reason I went back and did this is because I'm talking about a lot of things and a lot of stuff is going on right now. So I want to make sure you just understand the algebra. So literally, once we were given this picture, 3x minus 10, x minus 10, and 5, and we know that our volume is 1,435 cubic inches, then we just use this formula, V is equal to L times W times H, to come up with this. So now all I'm doing is the algebra required to simplify and get a solution. And since this is a constant, this is 5, and this ends in 5, I know that 1,435 is evenly divisible by 5. And once we did the division, which I'm okay that you do it in a calculator, but 1,435 divided by 5 is going to give us 287. I just don't want to take time to do I can't do it in my head while I'm talking, and I don't see any reason. So that's going to give us 287 is equal to 3x minus 10 times x minus 10. So we might very well be using factoring, or we could be using the quadratic equation. So again, we've got to multiply two binomials, which you can use the FOIL method or whatever method you want. And that gives us 287 is equal to 3x times x is 3x squared. 3x times minus 10 is minus 30x. Minus 10 times x is minus 10x. And minus 10 times minus 10 is plus 100. So I want this to be simplified on the right-hand side first. So minus 30x minus 10x is minus 40x plus 100. So now I'm going to move my 287 over here. When I move it to the other side, it becomes negative. That's the price you pay for moving it to the other side. So I have 0 is equal to 3x squared minus 40x minus 187. So can this be factored? So we have two options here, and I'm really sympathetic. So you might want to write this in the standard form. The standard form, it doesn't make any difference, and you might think, I don't need this, Kent, but some of you will. 3x squared minus 40x minus 187 is equal to 0. So compare that to ax squared minus bx plus c is equal to 0. And we have a is equal to 3, b is equal to minus 40, and c is equal to minus 187. So as it turns out, you can use the quadratic equation. You could use the discriminant. Remember, our discriminant is b squared minus 4ac. And if the discriminant turns out to be a perfect square, then I'm going to have two real solutions. But it turns out we can actually factor this. Let's do the factorization. And I'm going to I'm going to be honest with you right now. In a test situation, I would expect you to probably use the quadratic equation because you don't know if it can be factored and you don't have the time to mess with it. Here's our discriminant underneath. So you just simply plug and chug. Your A is 3, your B is minus 40, your C is minus 187, and you go. And then, there's going to be a lot of numbers. You're going to have to take the square root of a large number. You'll want to use a calculator. But I do want to show you that this one can be factored. So let's do the factorization method. So I draw a little tick. This is my method. You can use any method you want. And up here are going to be my x squared terms. Down here, my x term, and here is my constant. So I'm going to suggest 3x and 11 and x and minus 17 work. So I have to have 3x times x has to give me my 3x squared. This has to give me minus 187, and this has to give me minus 40. I think I said a while back that I was going to upload my, if you subscribe to my channel, which there's no reason for you to do, so what we do here is we multiply across. I filled in the answers, but we want my top row to be 3x squared. Then you skip to the end and put the constants term, and at the very, very bottom corner you put the middle term. So you have to fill in the boxes so that when you multiply across you get 3x squared. When you multiply across you get minus 187. When you multiply down, that's going to be 11x, and that's going to be minus 51x. And then minus 51x plus 11x is minus 40x. So we get the factorization 3x plus 11. The factorization comes from doing the kitty corner. 3x plus 11 is equal to x minus 17, and all of that is equal to 0. In other words, 3x squared minus 40x minus 187 is equal to 3x minus 11 and x minus 17. So again, if this were a test situation, I would expect you to just go ahead and use a calculator. The numbers are too big. I don't expect you to have a million different perfect squares memorized. And probably what I would do, I'm speaking about what myself, remembering when I was a student, what I would have done is I would just simply simplified it as much as I could, wrote it as standard form, ax squared plus bx, that should be plus. It doesn't matter, but it should be plus. And then find my value of a, b, and c, and then use the quadratic formula to find the value of x. Because looking at this, there is absolutely no way I'm supposed to know that this can be factored. I went ahead and factored it because if it can be, then it's much easier to solve. So we're going to solve this using the zero value theorem. So this is a times b is equal to 0. So we have a theorem that says if a times b is equal to 0, then a is equal to 0 or b is equal to 0. So that means 3x plus 11 is equal to 0, or x minus 17 is equal to 0. The last equation gives me x is equal to 17. The first equation gives me x is equal to minus 11 thirds. And minus 11 thirds is a negative value, and that doesn't make any sense. So we accept x is equal to 17, and we're asked what are the dimensions of the original? Well, I want to know my length and my width. So I found out that x is equal to 17. So this dimension right here is 17, and 17 times 3 which is 3x is equal to 51. So the length is equal to 51 inches. Okay, so let's just kind of think for just a second. I did an awful lot there. So I think this one, before I move to the next, it deserves a recap. So we're given the original problem, and we draw a picture. And we're talking about volume, so we're going to need the volume formula. So I note that volume is equal to length times width times height. You should be able to produce this picture I'm doubtful that some of you would be able to, so I would never give this to you unless figure 5 was literally provided to you. So once you have all of this, and you can look at the resulting, you take this sheet metal and you bend the sides up, because these have been cut out, these corners, and you can make a little box where the length is 3x minus 10, the width is x minus 10, and the height is 5. So since we want the volume to be 1,435 cubic inches, I just now go ahead and I plug those numbers in. Volume is equal to length times width times height. Volume's given. From the picture, I get my length times my width times my height. And from here on out, from here on down, all I'm doing is algebraic methods to solve this original equation. The one thing I will tell you, dividing through both sides by 5, you should absolutely do that. That would be something I would absolutely think, yeah, they definitely should see to do that. How you solve the resulting quadratic equation is up to you. You have to understand that you cannot solve 287 is equal to 3x minus 10 and x minus 10. You might be able to solve it if you knew that the side lengths were whole numbers. You could get some possible solutions. But the only way we can do it is to expand the right-hand side and convert it into a quadratic equation in standard form. That's what we have right here in yellow. Identify your A and your B and your C, and then you have to decide, how do I solve for x? Factorization is always a possibility, but you never know. You never know until you try it. If you do try it, it's easy. If you get the answer, it's easy. And in this case, we did. Otherwise, you plug and chug using the quadratic formula. I guess you could complete the square, but I know you're not going to be doing that. So let's go on to problem number 2 before this lecture gets really too long. So we have the strong version of the Pythagorean theorem. A triangle is a right triangle if and only if. So here I've drawn a picture. So we have that little bitty square right there denotes that's the 90-degree angle. The A and the B are called the legs of the right triangle, and C is called the hypotenuse. So a triangle is a right triangle if and only if the two legs squared, a squared plus b squared, and added together is equal to c squared. That's a really, really old piece of mathematics. We can go back and we can look at sherds of tablets in clay writing from the Babylonian era. And we see table after table after table of numbers a, b, and c, where a squared plus b squared is equal to c squared. So we know that they knew all about the Pythagorean theorem. So we're going to use it to solve this particular problem. A piece of property has the shape of a right triangle, so we're going to draw a picture. So let's get ready to draw a picture. So a piece of property has the shape of a right triangle. That's really convenient. So we'll draw just an arbitrary right triangle. And it doesn't have to be exact. So there we go. The longer leg, which would be this one down here, is 20 meters longer than twice the length of the shorter leg. So let's let x be the length of the shorter leg. So in my picture, that's going to correspond to this side right here. So a piece of property, the longer leg, which is going to be this one down here, is twice the length the longer leg is 20 meters longer than twice the length of the shorter leg. So it's twice the length of the shorter leg, which is 2 times x, because x is the length of the shorter leg, and then I'm adding 20 to it. The hypotenuse is 10 meters longer than the length of the longer leg. So the hypotenuse is 10 meters longer than this leg up here. So it's 30 plus 2x. So find the lengths of the triangular lot. So I want to find the value of x. Once I found the value of x, I can find the value. So the value of x is going to give me the length of this vertical side. But once I find the value of x, I can just plug in the value of x here and find the value or the length of this side. And then I can also find the length of the slanted side. But since this is a right triangle, if this is side A, and this is side B, and this is side C, I know that A squared plus B squared is equal to C squared. So setting this up is not going to be difficult at all. It's the algebra that's going to be hard. So A is equal to x, and we're going to square it. B is equal to 20 plus 2x, and we're going to square it. And C is equal to 30 plus 2x, and we're going to square that, and we're going to solve for x. So I'm going to remind you of a formula here. So way back in the day, we learned that A plus B squared is equal to A squared plus 2AB plus B squared. These are special products. And that A minus B squared is equal to A squared minus 2AB plus B squared. So let's use that here to help us out. So back over here, we're just going to simplify. So I'm going to start writing down here. I have x squared. So let's use this formula. 20 plus 2x is 20 squared, which is 400, plus 2 times A times B, plus 2 times 20 times 2x, plus 2x squared, which is 4x squared. Remember, 2x squared is equal to 2 squared times x squared, which is equal to 4x squared. Over here, 30 squared is 900, plus 2 times 30 plus 2x plus 2x squared, which is 4x squared. So what I'm going to do immediately, before I collect like terms, I'm going to go ahead and simplify each thing. So this is x squared plus 400. So we're literally all of the, setting it up is easy. It's just simplifying this. And it's not really hard. You just take it step by step. 2 times 20 is 40. 40 times 2 is 80. And 80 times x is 80x. And I'm literally going to leave my 4x squared there. and this is 900. 2 times 30 is 60, times 2 is 120, times x is 120x, plus 4x squared. And now I'm going to observe that I have 4x squared on both sides. So if I subtract 4x squared from both sides, then they vanish. So whenever you have a term, so if I move the plus 4x squared over here, it becomes minus 4x squared and they both disappear. So whenever you have a term, so what is a term? So here we have a sum. Sums are differences, and they're all positive. Each one of these are terms. X squared is a term, 400 is a term, 80x is a term. So whenever you have two terms on opposite sides of the equals sign that have the same sign, then they just cancel out. So my next simplification is going to be x squared plus 400 plus 80x. You could have got the exact same thing from subtracting 4x squared from both sides is equal to 900 plus 120x. Now I want this in the form ax squared plus bx plus c is equal to 0. That's the form I want. So I'm going to move the terms on my right hand side to my left hand side. So I have x squared, and I'm going to write the 800, sorry, not 800, but 80x term next. Then I'm going to subtract 120x from it. And then I'm going to write my 400 and subtract the 900 from it, and that's going to be equal to 0. So let's get some more space. So let's work on simplifying this. So that's going to give me x squared, and 80x minus 120x is minus 40x, and 400 minus 900 is minus 500, and that's equal to 0. So this, I think we can factor. This, if you want, you can identify ax squared plus bx plus c is equal to 0. And you're going to find that a is equal to 1, b is equal to minus 40, and c is equal to minus 500. But since this is a monic polynomial, we're going to try to factor it. So let's do it the right way. So let me draw my box here. Again, if you all have a different way to factor, you can do it. At the top here, I put my x squared, my first degree 2 term. Then I skip and put my minus 500, which is my constant term, and then I go back to the middle and put my minus 40x term at the bottom. So now what I want is pretty simple. I have to fill these two boxes with two values such that this value times this value gives me x squared. So I have to put x in there and x in there, and x has to be in each box. So x times x is x squared. And down here I have to put in two values that when I multiply them together I get minus 500. And the easy choice is minus 50 times 10. So minus 50 times 10 gives me minus 500. Now comes the hard part. Now we have to check. Now we multiply down. That gives me minus 50x, and x times 10 is plus 10x. And when I add them together, I have to get this value, and indeed I do. So I've got my box filled in, so all I have to do now is grab the factorization. So I do these little kitty corner things. So it turns out that we just discovered that x squared minus 40x minus 500 is equal to x, that's plus 10, times x minus 50. And that's equal to 0. And now that we've done it, it's really easy to solve. You're going to get the exact same answer if you go full Monty and use the quadratic formula. But this is going to be easy. This implies that x plus 10 is equal to 0, or x minus 50 is equal to 0. So the solution to the first is x is equal to minus 10, and the solution to the second is that x is equal to 50. So x in our original problem was the short side of a triangle, and we can't make any sense of a negative solution. So this is the solution that we use. X is equal to 50. So we're not done yet. So I know the dimensions of this side is 50 because x is equal to 50. But I have to find the dimensions of this side down here. So that's 20 plus 2 times x, which is 2 times 50. So that's equal to 120. And up here it's 30 plus 2 times x, which is 30 plus 100. So that is 130. So my triangle has side lengths 50, 120, and 130. And that is the dimensions or the answer that they were looking for. Okay, so we literally do only have 3 problems. Like I said, this is we only have 3 problems, but we kind of went into some detail. So here we have a formula, the height of a projected object. So this has been known since Isaac Newton. If air resistance is neglected, we're going to pretend like the air doesn't slow anything down. The height S, so S is a height in feet, of an object projected directly upward from an initial height of S0 feet with initial velocity V0 in feet per second is given by the following formula. S is equal to minus 16 t squared plus V0 t plus S0. So the right-hand side is a degree 2 polynomial in the variable t, where t represents the number of seconds after the object is projected. The coefficient of the degree 2 term, which is minus 16, is determined by the gravitational force of Earth as measured in feet per second squared. I know it's determined by that. It's not equal to it. If this were on Mars, that coefficient would be different. And V0 is the velocity of the initial velocity of the object that's being propelled upward. So if you can imagine you've got a slingshot and you've got a BB in it or a marble, and you shoot it into the air. When it leaves the slingshot, it has an initial velocity, and this will actually tell you how high it will get. So let's draw a picture once we have this. So we've got 2 things we have to do, and then we'll be done. And I'll kind of warn you. I will put again problem 1, problem 2, problem 3, and you can review what you need. If some of the other stuff interests you about dimensionality, if you're going to go into mathematics, we deal with infinite dimensional spaces all the time. So we have a projectile which is launched vertically upward from the surface of the Earth. So let's just kind of draw a picture here. So this is going to be the surface of the Earth, and we can imagine the projectile, it's going to be launched upward. It's going to go, and it's going to go, and it's going to go, and it's eventually going to come back and hit the earth. So we can find out questions related to this formula. S is the height in feet after t seconds. So in this case, we have our formula. S is equal to minus 16 t squared plus v naught, or v sub 0 if you wish, t plus s naught. So let me introduce to you. V naught is just a coefficient. It's just that variable choice. It's just a constant. It will be given to you. It's not a variable. The same is true of S naught. S naught is just some constant that is given to you. You have to figure it out. The variable is t. T is our variable, and it stands for time in seconds. So once you've been given the coefficient v naught, and it's given to you in the problem, and the constant s naught, and it tells you up there what they are, then if you can find out the height s by plugging in seconds. So I want to know the height after 0 seconds. Well, it will be a certain value. So that's what we're going to be using. So if a projectile is launched vertically upward from the surface of the Earth, so S naught is the initial height of the projectile. And the initial height is measured from the surface of the Earth. And in this case, you're actually standing on the Earth. So in this case, S naught is going to be equal to 0. It has an initial velocity of 100 feet per second. So that's our equation. So we're given by the problem S is equal to minus 16 t squared plus 100 t plus 0, where S is how high above it is, how high above the Earth's surface it is after t seconds. So after how many seconds will it be 50 feet above the ground? So in other words, they want to know if it's 50 feet above the ground, how many seconds will have passed? So we're solving for t. Now this one actually turns out to be a much easier problem than it seems to be at first. So let's use algebra and simplify this. 16 is divisible by 4, and 100 is divisible by 4, but 50 is not evenly divisible by 4. But 50 is evenly divisible by 2, and so is 16, and so is 100. So let's divide both sides by 2. So now I'm just doing algebra to make the solution easier. So that's going to give me slightly simpler 25, and minus 16 divided by 2 is minus 8, and 100 divided by 2 is 50t. So we're going to go ahead and put this into a quadratic equation form. So I'm going to bring the 25 over to the other side, leaving a 0 behind. And here we have an instance when I derive the quadratic equation. You'll notice my leading term is minus 8t squared. I don't like the negative, so I'm going to multiply both sides by a minus 1. So just so you understand what I'm doing, I'm multiplying 0 by minus 1, but it stays 0. But I'm multiplying all of this side over here by minus 1. So I have 0 is equal to 8t squared minus 50t plus 25. Is there anything else I can do to make this problem easier? Well, there's not, because the GCF of these three terms is 1. Now, if this were 26, I could divide through by 2 again, but it's not, but it's 25. So what we're going to do in this one is we're going to go ahead, and I'm going to indulge you, and we're going to use the quadratic equation. So the only thing you have to note here, this is a quadratic equation in the variable t. And if you want to write it this way, you can. So this is a t squared minus plus bt plus c is equal to 0. So my a is equal to 8. My b is equal to minus 50. And my c is equal to 25. So my quadratic equation says t is equal to minus b plus or minus the square root of b squared minus 4ac. All of that is over 2a. So that means t is equal to minus b. So b is minus 50, so minus minus 50 is 50. Plus or minus the square root of b squared, so minus 50 times minus 50 is 2,500, minus 4 times 8 times 25. All of that is going to be over 2 times a, which is 16. So again, just simplifying again, t is equal to 50 plus or minus the square root of 2,500. So 4 times 25 is 100 times 8 is 800 over 16. So that gives me that t is equal to 50 plus or minus 2,500 minus 800. Well, what's 25 minus 8? That's 17. So that's 1,700 over 16. So here is when you have to realize that 1,700 is, there are no perfect squares. So here's where you actually pull out your calculator to find the answer. It's 50 plus 41.2 over 16, or t, as this turns out to be, if my notes are right, we can check. Square root of 1,700. Whoops. Let's clear it. Square root of 1,700. And yes, I would expect you to use a calculator for this. 41.2, that's good enough. Or t is equal to, let me come on down here, or t is equal to 50 minus 41.2, all of that is over 16. So again, use your calculator, and you're going to get t is equal to 5.7, or t is equal to 0.55. So you're getting two answers. None of them are complex numbers, and none of them are negative. Which one do you throw out? Which one is right? Well, here math actually tells us something about math models the real world. So if we go back up to my original picture, I want to know how far. I'm going to say this is 50 feet off the ground. And this is the path of the projectile, okay? But 50 feet off the ground, the projectile hits that height in two different times. The first time, a small amount of time passes, wait, and a larger amount of time passes. So this point right here, it reaches this point right here at after 5.7 seconds. And it reaches the original height of 50 feet above the ground really quickly in about half of a second. Interesting. I think we have one more part of the problem. How long will it take for the projectile to return to the ground? So what is the height of the ground? It's 0, right? So I'm going back and literally just looking at this original equation right here, except, I'll come to the side, I want to know what it is when the height is 0. So my height S is 0. This is really simple and fast. 0 is equal to minus 16 t squared plus 100 t. And that's the same thing as we said earlier, is 0 is equal to minus 8 t squared plus 50t. I just divided both sides by 2. But this can be factored. The greatest common factor of minus 8t squared and 50t is 2t. Actually, before I even do that, I'm going to multiply through both sides so that my leading coefficient is positive. So I'm going to multiply both sides through. So I got to here, divide by 2. So when I divide 0 by 2, I'm going to get 0. And when I divide minus 16t squared divided by 2, I get minus 8t squared. And when I divide 100t divided by 2, I get 50t. And the next thing I'm going to do, since I have a slight preference, I like my leading coefficient to be positive. So to get to here, I multiplied, again both sides, by minus 1. So now I'm ready to do something. What is the greatest common factor of these two terms? Well, 8 and 50, oh, I can go even further, right? 16 divided by 2, oh, I can go even further, sorry. 4t squared minus 25 is equal to t. I should have divided by 4 because the GCF turned out to be 4, not 2. I discovered it at the very end, no harm, no foul. So now we ask, well, I divided that by 2 and then I divided again by 2. Should have stopped talking and started thinking. But you'll get it no matter at the end. There is no problem with doing it in 3 steps. even though you could have done it in 2, more elegant, but I didn't. So now literally the GCF of 4 and 25, that's it. They don't share any common factors. But the two terms do share a common factor of t. So that gives me t times 4t minus 25. And that's equal to 0. So it's factored. I have a factored solution. So that means this is the same as 0 is equal to a times b, where a is t and b is 4t minus 25. So the zero factor theorem says a is equal to 0, or b is equal to 0. So that implies, I said each of my factors equal to 0. T is one factor, 4t minus another one is. So t is equal to 0, which makes sense because it starts at the surface of the ground. And then 4t minus 25 is equal to 0, implies 4t is equal to 25, which implies t, I divide both sides by 4, is 25 divided by 4. That's the preferred fraction. You already know that this is just a little over 6 seconds. So it takes, if we go back up to my original picture, it starts out at 0 seconds. It starts out, it takes about 6 seconds to hit the Earth again. And that's completely consistent because it takes 5.7 seconds to hit this length. But here's the interesting and fun question. If I add, does it take the same amount of time to start from the Earth and make it to 50 feet above the ground as it does to take when it's at 50 feet to get down to the Earth? And it doesn't, because literally the difference between 5.7 seconds and 6 seconds is 0.3 seconds. But here it takes 0.55 seconds. The reason being is it's accelerating. Gravity's trying to keep it on the Earth. It's accelerating against gravity going in this direction. So it takes longer. Here it's more or less in free fall, we think. It is in free fall. So gravity is pushing it along and hurrying it along. Okay, that's it for this really long lecture. Again, you have the options of fast forwarding, reviewing, and looking at whatever part you need to look at.